Welcome to the final section of Math 0007. We're going to learn about groups in this section, so let's start off with the definition. To define a group, I actually need another notion, which is that of a binary operation. So a binary operation on a particular set X is simply a function from X cross X to X. For example, you know lots of binary operations. There is the plus function on R. Now, it may sound a little bit weird to think of this as a function, but it really is just a function from R cross R to R, because plus takes two elements of R and outputs another element of R. The only difference between plus and a standard function is the way we write it. So we don't write, for example, plus 2, 4 to be equal to 6. Instead, we usually write 2 plus 4 equals 6. But there's no difference between those two things other than a piece of notation. We use what's called infix notation when we write the plus in the middle like that. So all these things really are just functions. As another example, you know that the composition of two permutations is again a permutation, and that means the circle, the notation we use for composition, that thing is a binary operation on the set Sn of all permutations of 1 up to n. As another example, if you take the minus operation, that's a binary operation on z, because if you subtract an integer from an integer, you get another integer. So minus is a function which takes as input two integers and gives you as an output another integer. On the other hand, minus is not a binary operation on the natural numbers. Remember, a binary operation on a set X is a function from X cross X to X. So the output must always be an element of the same set X again. That's not true for subtracting two natural numbers. You can subtract two natural numbers and get something which is not a natural number. So for example, if you do 2 minus 4, that's a natural number subtracted from a natural number, but that is not an element of the natural numbers because they don't contain negative numbers. So it's not a binary operation on the set n. Okay, so we know many different binary operations. We're now going to use the idea of a binary operation to define the central character of this last part of 0007, which is a group. So here's the definition. You take a set G, and you take a binary operation on G, which I'm going to call star. Then we say that the set G together with the operation star, so we'll write G comma star like this, and often you'll see people write this, a comma around those brackets around those things like this. Sometimes I may even do it. We say those two things make a group, or alternatively we say G is a group under star if there exists a special element E in G such that the following three things hold. These three things are called the group axioms. So the first group axiom, called the axiom of the identity, or the identity axiom, is that for every G in G, we have E star G and G star E is equal to G. The second axiom, which is called the axiom of inverses, or the inverse axiom, says that for every little g and big G, there exists an H in G, such that H star G and G star H are both equal to this special element E. So that is the same element E as we were talking about in the identity axiom. Finally, the associativity axiom says that for all G and H and K in the set capital G, G star H star K must be equal to G star H star K. So those are the group axioms. Let's look very quickly at a very simple example of a group, which is that we take the set to be the integer z, and we take the operation to be plus. And this is a group. And the special element E in this case must be 0. So let's go through those axioms and see why they're true when the set G is the set of integers and when the binary operation star is the binary operation plus on the set of integers. First of all, the identity axiom, axiom 1, would say E star G and G star E must be equal to G. So in our case, that says 0 plus G and G plus 0 must be equal to G for all g in the integers. Well, that's true because adding 0 doesn't change what you add it to. Okay, so this one's certainly true. The next axiom, the axiom of inverses, well, in our case, it says that for every integer z, well, every integer g, let's say, there must exist another integer h, such that h plus g and g plus h are equal to the element e from the previous axiom, which is 0. And of course, that's true. You can just take h to be minus g. So if g is in z, then minus g is also in z, and g plus, let's get this the right way around, minus g plus g and g plus minus g are both equal to 0, which was the special element in the previous axiom, in the axiom of the identity. So z together with the binary operation plus also obeys the second axiom, the axiom of inverses. You can also see why it's called the axiom of inverses here. Minus g is often called the additive inverse of g. And finally, if we look at the associative axiom, again, this is obviously, well, not obviously, but it's true for z and plus because addition on the integers is an associative operation. A plus in brackets b plus c is always equal to brackets a plus b brackets plus c for any integers a, b, and c. So that means z together with addition obeys the associativity axiom, so it obeys all three of those axioms, and it's therefore a group. Let's say a little bit about the terminology that we use when we're talking about groups, before we see some more examples. So first of all, any element E satisfying the identity axiom is called an identity element in G. So for example, in the group Z plus, 0 is an identity element. And in fact, what we're going to show later on in the next video, in fact, is that there is one and only one identity element. So any group can only have one special element E obeying the identity axiom. Secondly, we'll refer to the binary operation in the definition of group in several different ways. So it's called the group operation, or sometimes called the group law, and it's sometimes called the multiplication law. So often, to help us gain fluency in manipulating elements of groups, it's useful to use some of the algebraic skills we already have based around multiplying numbers. So many of the rules that apply to multiplying ordinary real numbers also apply inside groups. So we'll often write, in fact very often, write GH in a group when what we mean is G star H. So we omit the binary operation, the name of the binary operation, and we implicitly just write G next to H instead of G star H. So that's just like in ordinary multiplication of numbers. You'll often write XY instead of X and then a multiplication sign and Y. Well, we do precisely the same thing in groups because it makes writing out our arguments a lot simpler and quicker. Finally, we talk about the order of a group to refer to the size of the set capital G. So if you have a group G with under a binary operation star, then the order of the group just refers to the size of the set G. And we say that G is a finite group if the size of that set is finite. Otherwise, we say that G is an infinite group. So let's return to some examples of groups. I want to convince you that you actually already know many, many examples of groups. First of all, we've already done this one. The set of integers together with the binary operation plus is a group, with the identity operation being 0. Next, let's take Sn. So you'll remember that Sn means the symmetric group on n letters, which is the set of all permutations of the set 1, 2, 3, 4 up to n. We also know that composition is a binary operation on Sn. We discussed this on our first slide this lecture. And in fact, Sn together with the composition operation is a group whose identity element is the identity permutation. So let's think why this is. Remember, to be a group, you have to pass 3 axioms: the identity axiom, the inverses axiom, and the axiom of associativity. So let's do them one by one. First of all, the identity operation, the identity axiom. Well, if you take E in the group axioms to be the identity permutation, then for any S in Sn, S composed with the identity and identity composed with S are equal to S. So that means the identity axiom is true for Sn together with the binary operation composition of functions when the special element E is the identity permutation. Next, we have to think about the inverses axiom. But we know that the inverse of a permutation is a permutation again. So if S is in Sn, then S inverse is in Sn too. It's a fact from when we learned about permutations. The inverse of a bijection is a bijection again, so the inverse of a permutation is a permutation. And S composed with S inverse, well, by definition, that is the identity permutation, which is the identity element in our group, Sn. And that's the same as S inverse composed with S. So it's true that for every element of Sn, there exists another element of Sn, such that when you combine those elements using the binary operation of composition, either way round, you get the identity. So we've passed the inverses axiom. And finally, usually the hardest or the trickiest axiom to check is associativity, because it's a property of 3 different elements of your would-be group. But here it's very easy because we know that function composition is always associative. So this one we get for free. Function composition is always associative. So certainly the special case of composing 3 permutations is associative too, and therefore we've checked all 3 axioms, and Sn together with the binary operation of composition of functions is genuinely a group. So let's look now at an example of something that's not a group. Let's say you take the real numbers r together with the binary operation of multiplication. Now, multiplication really is a binary operation on r, because if you multiply together any 2 real numbers, the answer is another real number. But it's not a group. So let's see why not. Well, it does have an identity element, namely 1. If you multiply any real number by 1 on either side, you get the same real number you started off with. So 1 is an identity element there. It passed axiom 1. But axiom 2 is where the problem is. And the problem comes when we think about the number 0. Number 0 doesn't have an inverse under multiplication because there's nothing you can multiply 0 by to get the identity 1. So the identity element, if r cross r together with multiplication was a group, would have to be 1, because that's the only number which satisfies that when you multiply it by any number, you don't change that number. So if r together with multiplication was a group, then its identity would have to be 1. But then axiom 2 fails because there's no number you can multiply 0 by to get 1. So the problem is the identity axiom doesn't hold because there is no, the inverses axiom doesn't hold because there's no inverse for 0. You can't multiply 0 by anything and get 1. But that really was the only thing that went wrong. The only problem that stopped R together with multiplication being a group is the failure of the inverses axiom for the number 0. So as we've seen, there is an identity element, and of course multiplication of real numbers is associative. The only problem is the single failure of the inverses axiom when we thought about the element 0 in R. So that means we can fix this. We can find a group which consists of real numbers and where the group operation is multiplication. The only thing we have to do is throw out 0. So here R, take away 0, so this is that backslash is the set difference. It's the set of real numbers which are not equal to 0. That thing is a group under multiplication. And in fact, there's some special notation for this. We often write R superscript times to mean R without 0. And we'll extend that notation as well to the complex numbers. So we'll also write C cross to be the set of complex numbers which are not equal to 0. Okay, one last useful concept for groups is that of a Cayley table or a group table, or sometimes even a multiplication table for a group. So let's say you have a group G where the group operation is written with a star. And the Cayley table for that group has the rows and columns labelled by the elements of G. And they have to be the same order, so the same order in the rows as they were in the columns. And then what you do is in row X and column Y, you write the result of combining X and Y using the group operation. So it's important to do these in the right order. The convention is that in row X and column Y, we put X star Y. In general, X star Y might be different for Y star X, like in the symmetric group Sn, for example. So it's important to get that the right way around. So here's part of the group table for the group consisting of the integers under multiplication. You can see I've labelled the columns by the elements in the group. And you can see that I've labelled the rows by the elements in the same order. So 0 and then 1 and minus 1 and then 2 and minus 2 and so on. The same order in the columns as in the rows. Now of course for a group like this where it's an infinite group, you can't write down the whole Cayley table. But if you have a finite group, it's possible to write down the entire table. And then what that gives you is absolutely everything that you could, absolutely all the information you could possibly know. G is somehow contained in that table because it contains complete information about how the multiplication or how the group law works in that group. So you can see here, let's just look at some of these entries, like in the entry in row 1 and column 2, what I should put is the result of 1 plus 2, which is 3. And in row 2, let's say row minus 2 and column minus 1, I should put the result of minus 2 plus minus 1. Of course, that's minus 3, so that's why there's a minus 3 there. So as an exercise, let's do what I've suggested down there is you have a go at finding the group tables for S2 and S3. So write that down just to get familiar with the idea of a group table and with doing multiplications, products in a group. So I'm going to do the S2 table actually. So let's do the S2 table. So we'll draw up the table. Oops. And in the table, we have to have 2 rows and 2 columns, 1 row for each group element. So there'll be a column for the identity and then for the other element of S2, which is 1, 2. And here I have to put the identity in 1, 2, so the same order. Often when people draw these Cayley tables, they'll put the name of the operation in the top left square here. So let's do that here. There was a plus. There was a composition symbol there, and we'll put a plus there. And then in row 1, well, row 1 is the row of the identity operation. So of course, row 1 is just going to look like the labels for the columns, because composing with the identity doesn't do anything. And of course, column 1 will look the same because composing on the right with the identity doesn't do anything. And the only interesting element in this group table is what goes in the bottom right entry. So in there goes 1, 2, composed with 1, 2, and of course that's the identity. So this goes right here, and in there we put the identity. So there's the complete group table for S2, and you should have a go at S3 next.